when the announcement was made. I was watching it on live stream at a laboratory in England, along with many other scientists. And Peter, of course, was there at CERN in the auditorium. What was our reaction? I mean, my reaction as a scientist looking in from the outside to this, it was extremely moving. Something that we had in our hearts believed and hoped for so long, to realize that that is actually how nature really works, that you have somehow caught nature at it. So although I wasn't physically present in the room, in real time, we were all watching on the screen with the other scientists, and we were all feeling the same feelings. And I think whether I said it in the book or not, I said I would have been hardly surprised at that moment if a thunderbolt had come through the roof of the CERN auditorium, and Charlton Heston, playing the role of God, was berating humans for having trespassed where we had no right to be. It was that you have somehow touched the fundamental workings of the universe. And on this particular occasion, that is almost literally the case, that these are the fundamental things, the nature of nature itself. And Higgs and others were caught on the cameras at the time, sort of wiping tears from their eyes. It was that sort of emotion.
Frank Close is a Fellow of the Royal Society, Professor Emeritus of Theoretical Physics at Oxford University, and author of many books popularizing science. He's written The Infinity Puzzle, Neutrino, The Void, Antimatter, Theories of Everything, and most recently of all, his latest book is Elusive, How Peter Higgs Solved the Mystery of Mass. And that's due to be published next month to mark the 10th anniversary of the discovery of the Higgs boson at CERN on the 4th of July, 2012. So, Professor Close, thank you very much for joining me today.
Hi.
When we say that Peter Higgs discovered the mystery of mass, what exactly do we mean by that? What do we mean by mass itself in this context?
Well, what he showed, it turned out, was that mass isn't some intrinsic property of things. It's the result of things interacting with the cosmos at large. But first of all, mass is, we first meet it in Newton's equations of motion, that the bigger the mass a thing has, the harder it is to make it move. That force applied to something accelerates it, and the amount of acceleration is proportional or inversely proportional to the mass of the object. So big masses hard to move, little masses relatively easy to move. And the concept of mass that we're used to in the world at large is the same concept that we apply to particles that we find in atoms, that if you kick a lightweight particle like an electron with a certain amount of electrical force, the amount of acceleration it will have can be quite large. Whereas if you hit a heavy particle like a proton with the same amount of electrical force, the amount of acceleration it will have will be smaller.
So is the mass that I mean, I've had some training in physics, but my understanding of mass is that it has inertia, as you've said, it has an attractive force between other masses. Is that the kind of mass that that we're talking about at the particle physics level, and that the mass that Peter Higgs has uncovered the mystery of?
Yes and no, to give a sort of confusing answer. What Higgs found is the way that the mass of the basic particles arises. By basic, I mean those such as the electron that have no deeper structure, at least not as far as we know. So the electron gains its mass through this effect, and the quarks, which are the seeds of the protons and neutrons that build up atomic nuclei, gain their mass by this effect. But mass at large, as you and I perceive it, is mostly the result of the mass of the atomic nuclei inside the atoms of our body. And that mass comes mostly from the kinetic energy of those quarks as they jiggle around inside the nuclear particles. So mass in bulk has almost nothing to do with the Higgs effect. Size does, and structure does, because the mass of the electron sets a scale for the size of the simplest atoms. For example, the size of a hydrogen atom, which is a single proton at the middle with a single electron on the outside, if the electron was much heavier than it is, the atom would be smaller. If it was lighter than it is, the atom would be bigger. And if it had no mass at all, the atom would be infinitely big, which would mean it wouldn't exist. So the fact that the Higgs mechanism gives rise to the mass of the electron is one of the ingredients that sets the scale of the size of structures. So your overall mass or weight doesn't have much to do with the Higgs business, but your size does.
Right. I hadn't realized that. I hadn't realized that the mass of protons and such like that was due to the quarks moving, and that you've got, of course, Einstein's famous equation of E equals mc squared. So presumably the mass is coming from the kinetic energy, which that's equivalent to.
Exactly right. I mean, the mass of a proton at rest, by Einstein's equation, as you said, E equals mc squared, that mass gives it a certain amount of energy even at rest. And that energy originates from the motion of the quarks inside the pieces.
Can we move on to the question of bosons? Because bosons have something to do with forces, as I'm aware, and the discovery of which made Higgs famous was the discovery of the Higgs boson. Can you explain to us what bosons do and how they're connected with forces?
Well, all fundamental particles are divided into two classes called bosons or fermions, named after two famous scientists, Bose and Fermi. And these two classes reflect the way that particles behave under the rules of quantum theory. And to sort of give a homely analogy, fermions, like the electron and the quarks, are like cuckoos, where if you put two in the same nest, that is one too many. Whereas bosons are like penguins, the more the merrier. They like to sort of collect together in large numbers and cooperate. So, for example, photons, the quantum particles of light, are bosons, and you can put more and more photons together and make ever more intense beams of light. Higgs bosons are likewise particles, we now know, that have this affinity for one another. And although we have so far only discovered the existence of the Higgs boson, and I think we'll probably talk later on what is it we want to know more about, one of the things we want to know more about is how is it that these multiple Higgs bosons cooperate together like penguins to make the whole, what we call the Higgs field in which we're immersed.
Okay, so there's a connection there between bosons and forces. Is that right?
There is, but let's be careful that the Higgs boson is unusual compared to the bosons that we've been familiar with. You're right that one of the profound insights that has come from quantum field theory over the last century has been that forces, such as the electromagnetic force, for example, are transmitted by the exchange of particles called bosons. And these particles have an intrinsic spin, which makes them what's called vector bosons. The photon is the example in the case of the electromagnetic force. The exchange of photons between electrically charged particles transmits energy and momentum from one particle to another and forces it into an acceleration, namely it transmits the electromagnetic force. We know of other short-range forces in and around the atomic nucleus called the strong force and the weak force. And the strong force is what holds the nucleus together, and the weak force gives rise to a form of radioactivity that causes nuclei to change their form, such as the way that hydrogen turns into helium in the sun, for example. And we now know that these forces also are carried by vector bosons. In the case of the strong force, which really isn't the main theme today, they are carried by particles called gluons, which glue the quarks together to build up nuclear particles. And in the case of the weak force, which is very much key to what Higgs eventually has led us into, they're carried by what's called the W and Z bosons. W for weak, and Z, well, the W for weak bosons are very massive. They carry electrical charge, and they have an electrically neutral partner called the Z. Z for zero. So the W and Z bosons are very massive. They transmit the weak force. It is a very short range force, whereas the photon is massless and transmits the electromagnetic force, which is a long range force. So that's what bosons, vector bosons, or technically gauge bosons, to give a jargon to them, do. They transmit forces, the ones we know. The Higgs boson is indeed also a boson, but unlike these, it doesn't have any spin. The Higgs field has no sense of direction, whereas an electromagnetic field does. You can have a north and south pole pointing this way or that way and so on. So the Higgs field, whatever it is, has no sense of direction. And by analogy, an electromagnetic field, if you pump in energy, can burst into light, electromagnetic waves, which in quantum theory are photons. Likewise, if you pump energy into the vacuum, the Higgs field, it can bubble up into Higgs bosons. The quantitative difference is that I can just flick a light switch and turn on millions of photons just like that. Whereas to produce even one Higgs boson, I have to have the full energy of a high energy particle accelerator, such as the Large Hadron Collider at CERN. The Higgs boson has no spin. It is not a force carrier in the sense that the photon and the W and the Z are, but it clearly has influence on things. In particular, when other particles interact with it, that is what eventually gives them the property that we recognize as mass. So in a sense, the property of mass is what these particles gain as a result of trying to work their way through this mysterious Higgs field that we're immersed in.
Right. So, I mean, it's interesting that, you know, you can generate photons very easily. Strike a match and you've got a whole pile of photons suddenly appearing. But to get the Higgs boson, you need to get something massively powerful like the Large Hadron Collider. Now, where does the trying to put this in a way which doesn't sound too facile, but where does the Higgs boson actually come from? Is it because we have a field which is just everywhere present, the Higgs field, and by using the energy from the collider, we can pull out of that field something like the boson? Is that how it's happening, or have I got the picture wrong here?
I think that's a very good description of it. But to back up one stage, we're talking about this Higgs field. The radical insight that Higgs and others had back in 1964 was that if you remove everything from space and were left with a perfect vacuum with, in a sense, nothing in it, that would actually be unstable. But if you add to this nothingness...
Sorry, when you say it's unstable, it's hard to imagine how nothing left behind could be unstable. What would it be unstable into if there was... I mean,
let me explain what happens, and then we can.
Sorry, you go ahead. Yeah, sorry.
That if you add to this state of nothingness this weird stuff which we call the Higgs field, that makes it more stable. Now, sort of to answer your question, or like a politician would be to bypass it, with the idea that by adding something to nothing, you end up with something that is more stable, is completely counterintuitive. But that is part of the magic of the whole thing. That is the key feature, perhaps, which, because probably up to that moment, the question as you posed it is the completely natural thing. Nobody had really imagined things could be like that. But we now know that indeed a vacuum without the Higgs field will be less stable than a vacuum with the Higgs field.
Right. And presumably there are many Higgs bosons flying around in space all the time, constantly, you know, trillions, I suppose, of them. But where are they, in the sense that if it takes a large hadron collider to pull one out and show it to us in its kind of for a billionth of a billionth of a second, where are they normally if they're not visible in that sense?
Well, in the jargon, we would say that they've condensed to make the field. Let's go back one step. That's I don't know what the Higgs field is made of. I just know that it is there. So when I say these words, they are words which at a certain point are expressing a state of ignorance, but nonetheless, we know we are immersed in this weird stuff. We call it the Higgs field. Now, in order to make one of these bosons bubble out of the field, you have got to supply a huge temperature, or essentially a huge energy. In particle physics terms, it's 125 billion electron volts. And if I converted that into temperature, it's 1 followed by a lot of zeros. I mean, I'll get it wrong if I try to guess the number. So it corresponds to a vast temperature. Now, that is the sort of temperature which has not existed in the universe since the first trillionth of a second of the Big Bang. So within that first instant after the Big Bang, yes, there were zillions of Higgs bosons bubbling around, and the universe rapidly cooled, and these things condensed to make the Higgs field. Whether there are Higgs bosons bubbling around in the universe today, well, quantum theory says there will be fluctuations happening all the time. So yes, they are out there, but in practice, unless you found some local region whose temperature was trillions and trillions of degrees, there would not be Higgs bosons bobbing around there. It's possible the only place in the universe nowadays, if that's the right word, that has these sort of temperatures is when you collide these particles in the Large Hadron Collider. What we are doing in effect there is to take a journey back in time. In a sense, we are recreating in those experiments the conditions that the universe itself experienced just after the Big Bang, when the Higgs bosons were indeed very common.
Can you detect the Higgs field as it stands as a field itself, a bit like the ether? Can you detect that? Well, you know, they tried to do that with Michelson-Morley experiment, but is there some way of detecting the Higgs field without necessarily having to produce a boson from it?
Well, the answer is the latter question, yes, though we haven't done yet. But let's just go back to the first one, because you made an interesting remark about the ether.
Yeah.
And this is actually one of the ironies to my mind, which is that, in a sense, the discovery that we're immersed in the Higgs field is very much like the idea that we thought we'd done away with, namely that there is a sort of ether out there. So how is it that we've always been taught that there isn't? Well, the irony, or one of the ironies, is that two things. The mathematics of the Higgs field, it turns out, in a very profound way, satisfy the constraints of relativity, but put that on one side. More directly, that the Higgs field, when particles interact with it, they gain a mass. Particles without mass do not interact with the field. What is the most famous particle without a mass? The photon of light. So the great irony is that those experiments that Michelson and Morley were doing in the 19th century by shining rays of light and reflecting them off mirrors were using the one probe to which the whole Higgs field is completely transparent. So there's a great irony in that. Now, so where are we with trying to understand the Higgs field? Well, to draw, again, an analogy that I think I do in the book, that we're immersed in the Higgs field much the same way as fish are immersed in water. The fish need the water to be there. And what we have achieved is a bit like some very clever fish who have managed to do some experiments on their surroundings, probably by boiling it up and boiling the water around them, and discovering a single molecule of H2O. So by that discovery of that single molecule of H2O, which is analogous to us having found the Higgs boson, they know the water is there. But the real challenge for them is to understand the nature of the oceans, which is for us the challenge of understanding the nature of the whole Higgs field. Yeah. And the first step towards that would be to see how two molecules of H2O came together to start building up water at large. And for us, the step would be to see, can we, in a single collision of particles at the Large Hadron Collider, produce two Higgs bosons? And if we're lucky, those two Higgs bosons interact with each other before they escape the apparatus. And that is what we hope we will begin to start understanding in the next few years, following the new upgrade that has just been done at CERN. So if we can start seeing how pairs of Higgs bosons are produced and interact with each other, we might begin to get the first stage of understanding how Higgs bosons collectively build up this ether, if you like, that we call the Higgs field.
But you put me in mind of an old quotation from Isaac Newton when you mentioned that there's still the unexplored field out there, which is all beyond us, because he said at one time that he felt himself like some child playing on the seashore, picking up a stone here or a bright pebble there, while the whole ocean of the unexplored world lay in front of him. And it's a bit like that by the sound of it. We've been able to knock out a Higgs boson here or there, but being able to go further than that looks like there's a huge uncharted territory before us.
That is certainly true, but let's not fail to realize where we've reached in this. For 50 years, we had the theoretical belief, if you like, suspicion, expectation that the ideas that Higgs and others had created back then indeed showed how the universe works because of other experimental consequences that they had led to. But until we had actually done an experiment which produced a Higgs boson, which showed that indeed these ideas were not just some mathematical trickery, but that they were actually expressing concepts that the universe itself somehow reads. Until that moment, this was all theoretical. And so 10 years ago, in July, we produced the Higgs boson, which confirmed that these ideas are indeed how nature works. And in a sense, completed a 2,000-year chapter in the search, not just for the fundamental particles of matter, but an understanding of why they are as they are. And we now know they have the mass because they are immersed in this stuff. And that is remarkable cultural insight, that we are immersed in some weird stuff. I mean, the question you posed earlier, how can it possibly be that if you've got nothing that is unstable, and to stabilize it, you add something? Remarkable phenomenon. And we now know that is how the universe is. And what it implies, well, that's for the future. But it's a tremendous cultural step that has been taken. And I don't think we should sort of start thinking, oh, but we don't know this, we don't know that. Well, of course, as scientists, that's what we always think. The moment we discover something, we want to know where we go next.
There's always another question.
There's always another question, yeah. But at least here, I think the first questions of how do Higgs bosons form the Higgs field, because we don't have an idea, as I said earlier, what the Higgs field actually is. We know what it does, but we don't, and we know how much energy it takes to make it bubble up into bosons. But beyond that, we know nothing. And we don't know, for example, whether it has no structure of its own, or whether if we were able to look at it with a very fine microscope, even more powerful than we currently have, we would discover the Higgs field also has internal structure. After all, the course of history has always been that when we improve the power of our experiments, we discover that what at one layer of the cosmic onion we thought was the final layer, we turn out and discover that there is structure and dynamics inside. And so whether the Higgs field itself has dynamics inside, we don't know. And there's one final thing of excitement about the Higgs field, which touches upon cosmology, that if we think of the Big Bang itself, in the literal first instance, there was this phenomenon which is known as inflation, that the newly born universe suddenly inflated exponentially in a fraction of a second. And the dynamics that caused that, we don't know at all where that came from, except for one thing. From the uniformity of the universe overall in all directions, we know that whatever drove this had no sense of direction. And in quantum theory, that means it was driven by a field whose quantum particle has no spin. The very properties that the Higgs field itself has. The Higgs boson has no spin. So could the Higgs boson be also the entity that drove the inflation in the early universe? Well, that's a fair question to ask. Given what we know about it at the moment, the answer is no, but for the following reason, that what drove the early universe's inflation was something that couples very powerfully to gravity, because that is what was inflating it out. Now, the Higgs boson has essentially no coupling to gravity. I mean, it's so trifling you couldn't even know how to start measuring it. It is infinitesimally small. But thanks to quantum mechanics, there are ways that maybe gravity could, through a stepladder process, talk to the Higgs boson. That the Higgs boson likes to couple to massive things. The more massive they are, the more affinity the Higgs boson has for them. So if there are supermassive particles out there waiting to be discovered one day, although we can't produce them at the moment in an experiment, thanks to quantum uncertainty, they are bubbling in and out of the vacuum all of the time. So there is the possibility that the Higgs boson might couple through these supermassive particles which fluctuate in and out of existence. And if they're really massive, that might enable the Higgs boson to influence the gravitational interaction. So it depends what we find out about the Higgs boson in the course of the next years as to whether these possibilities may or may not have any relevance at all.
I was going to say, are we hinting at dark matter here, the thing which is out there or postulated to be out there, and we don't know what it is? Is that what you have in mind?
That is if dark matter is a real phenomenon, rather than being an indication that there is something missing in our understanding of gravity. But if indeed, if you might say, the most conservative solution is that there are massive particles that do not shine in electromagnetic radiation, then if these things are indeed truly massive, they will have an affinity for the Higgs boson, and they could play a role. But they would have to be exceedingly massive to link the Higgs boson into gravity and inflation. But who knows? It is possible that they are supermassive. That, other than the fact that to understand the galactic structure and the cosmos overall, that there has to be this dark matter made of dark particles. Other than the fact that these dark particles are massive, we don't know how massive. They could be exceedingly massive, and in which case it could be that all of these things come together. The Higgs boson couples to gravity and drove the universal inflation thanks to these supermassive dark particles which are waiting to be found. Possible.
Coming back to your book, I mean, one thing which struck me is it's split up into three parts. So the first part is a bit about the theory and making that understandable to pretty well everyone, you know, the aim of that. The second part, though, is being on the track of trying to discover the boson and leading up to the Large Hadron Collider in CERN. And I wonder, I mean, you've been involved in this quite personally for quite some time. I know you spent many years talking to Peter Higgs and interviewing him and being at the forefront of that kind of thing. What was it like on the, I mean, you presumably you were there on the 4th of July 2012, and what was that event like at that time?
Well, I actually wasn't there on the 4th of July. What happened was that I had the previous 10 days been at a summer school in Sicily, and Peter Higgs was there. And it was during the time of that summer school that the decision was taken at CERN to make an announcement on the 4th of July. And although none of us were told what the announcement was going to be, because in fact, apart from the Director General of CERN, there was not an individual on the planet who knew the full story of what exactly. There were two major experiments that had been searching for this thing for a long time, and although within an individual experiment they knew what their evidence was, they did not know what the other experiment's evidence was, and vice versa. The Director General was the only person who was aware of that. So it didn't take a huge amount of intelligence to realize that the DG would hardly have decided to have this announcement on the 4th of July, including inviting all former living DGs to be there on the day, along with Higgs and others who had worked on this idea, if they're going to say, we haven't found anything. So that was sort of quite positive. As a result of that, while we were in Eritrea having lunch, Peter received a phone call from a scientist at CERN saying, I think you should come over here rather than going straight back to the UK. And so Higgs changed his travel plans to go to Geneva. And this created some problems because his travel insurance actually was due to expire on the 3rd of July, the day he would have gone back. He didn't have any Swiss francs with him either, but you know, these are the problems that arise when you are about to make a major scientific discovery that's going to give you a Nobel Prize. So he changed his travel plans. And one of the things that he in particular has always been worried about is the media, because he's a very shy, retiring person. One of the surprises that I had, incidentally, and I mentioned it in the book, at the end when I was asking him what his reactions had been to all of this, he said it ruined his life.
I was going to ask you about that, yes. What did you make of that?
And well, it shocked me at the time. I thought, you know, how can it be that you have written equations which turn out to be the very equations that nature uses, and you have then seen 50 years of effort put into pursuing this idea, and finally it's vindicated with a discovery. I mean, the idea that you have been able to find how nature works is remarkable feeling for any scientist, and then to get a Nobel Prize at the end of it, how can this be ruin? And well, I would have to probably read the actual quote in the book so that I don't mispresent it. So if you can give me a second, I'll find it, because it's at the end of the main part of the book. And yes, so here it is. To be sure I had not understood, I asked him again the next time we spoke. He explained, my relatively peaceful existence was ending. I don't enjoy this sort of publicity. My style is to work in isolation and occasionally have a bright idea. So that was his sort of long-term reaction to this. But partly with that in mind, a photograph of Peter Higgs and myself was taken at Palermo Airport, he having checked in to go to Geneva and I having checked in to go back to London. And we put an announcement out on Twitter to sort of give the impression that Peter Higgs's travel plans were sort of different than they were in reality, so that when he arrived at Geneva, hopefully there wouldn't be paparazzi already waiting for him. So the next day, sorry, 2 days later, the 4th of July, when the announcement was made, I was watching it on live stream at a laboratory in England, along with many other scientists. And Peter, of course, was there at CERN in the auditorium. What was our reaction? I mean, my reaction as a scientist looking in from the outside to this, it was extremely moving. Something that we had in our hearts believed and hoped for so long, to realize that that is actually how nature really works, that you have somehow caught nature at it.
Yeah. I have to say, sorry to interrupt, but your account of leading up to that announcement, although I wasn't there at the time, I was taken along with your excellent descriptions of how this was brought about and how it culminated in this announcement of CERN. And I found it moving just reading your account. So I mean, to be there at the time must have been even more so.
Yes. So although I wasn't physically present in the room, in real time we were all watching on the screen with the other scientists, and we were all feeling the same feelings. And I think whether I said it in the book or not, I said I would have been hardly surprised at that moment if a thunderbolt had come through the roof of the CERN auditorium and Charlton Heston, playing the role of God, was berating humans for having trespassed where we had no right to be. It was that you have somehow touched the fundamental workings of the universe. And on this particular occasion, that is almost literally the case, that these are the fundamental things, the nature of nature itself. And Higgs and others were caught on the cameras at the time, you know, sort of wiping tears from their eyes. It was that sort of emotion. He was then overrun by media. After the presentation of the results in the main auditorium, there was a press conference just across the hallway, which involved a walk of 10, 15, 20 meters from the auditorium to the council chamber where the press conference would take place. And he was completely mobbed. He had two CERN staff trying to clear the way through cameras. And one of these said to me that they, for the first time, felt, you know, how Princess Diana must have felt when she was always being mobbed by media. And throughout the whole of the press conference, Higgs didn't say anything other than to keep saying, "This is the day for the experimentalists, so I don't want to make any comment." And it was clear that he was very disturbed by this. I don't think, well, none of us anticipated, and he, right at the heart of it all, certainly never anticipated quite the huge human impact this discovery and the announcement had. I mean, Higgs had become almost a trade name, a brand. And why it was that Higgs created so much public attention when the man himself was so sort of retiring is one of the paradoxes of the story. I mean, I conjectured at the end that the name Higgs itself is so ordinary. It is like a symbol of yeomanry, the good British worker from the 13th, 14th centuries. That's Higgs. If it had been a name like Einstein or Dirac or something like, or Rutherford, you know, that is the sort of name that scientists have. But Higgs is, if Higgs can do this, you can do it. That sort of feeling to it.
I know that you've entitled your book Elusive, and I got a feel of a dual role for that, because not only is the Higgs boson an elusive piece to get hold of, which eventually, after, I mean, the papers were written in '64, it wasn't found until 2012, an elusive particle. But Higgs, the man himself, comes out being as an elusive character too. Doesn't have a television or a mobile phone or internet, and difficult to get hold of. And yet such a retiring man now thrust into the very center of celebrity must be quite difficult for him.
I think that is certainly true. I mean, you got the title absolutely correctly there, that the elusive referred both to the quest for the particle and the man. And yes, he has no television at home. He doesn't use the internet at all. He doesn't use a mobile phone. The only ways I had to contact him were physically to go to see him in Edinburgh, which in fact I had done in the past. But of course, the moment the lockdown arrived, which was just when I was beginning to start getting this thing together, we couldn't even travel. So I could write a letter and trust the GPO to deliver it, but as you know, nobody was doing anything. So you telephone his landline, and of course he doesn't answer, because his first security level is just to leave everything on the answer phone. So I would call him, arrange a time for us to have a chat, and this tended to be a Friday night or a Saturday night, and then he would call me at the prearranged time. And we actually spent the months of the lockdown talking for maybe 1 or 2 hours each week on the phone, with me then rapidly transcribing between calls and trying to understand where I wanted to go next and so forth. so in a strange way, certainly for me, and I hope also for him, it was sort of therapeutic, this whole business, actually having somebody that one was talking to, apart from those who you immediately were living with, and doing this project together. So the project itself turned out to be quite elusive because of that. But his retiring nature, and the way that this whole episode, he had to live through it, it would be too strong for me to say I sort of felt sorry for him, because you can't feel sorry for somebody who all this has happened. But I sympathize very much with the things that have been landed upon him. For example, when the Large Hadron Collider, well, it was clear in the 1980s that in order to produce the Higgs boson, you were going to have a machine much more powerful than anything that currently existed. And the Americans started designing something called the super collider, and that was just going to produce the boson by brute force. And all went well until after they dug about a quarter of the tunnel, the American funding agencies, Congress, just pulled the plug on it. And that meant that the Large Hadron Collider would be the only means possible, supposing even that we were going to be able to fund and build the Large Hadron Collider, because this was a consortium of many member states, including Britain. And back in the 1980s, early 90s, the 80s certainly, British attitude towards big science was very questionable. Lots of questions were being asked, rightly, about the way funding should be apportioned and so forth. And the Large Hadron Collider collectively was going to be talking of the order of 10 billion euros in equivalent currency. So this was no small business. Now, the Large Hadron Collider was being designed to do many things, of which the Higgs boson search was one. But in the public mind, the Higgs boson gained a bigger and bigger presence. And Peter Higgs himself then became the person whose name was attached to this. And one of the things that he said to me that when we were having our conversations was that this concern worried him very much, because there had been so much attention paid to the boson that now he had found it, he felt that it was going to be easy for people to say, well, we found the boson, that was what it was for, we can turn the machine off. Whereas in actual fact, that was just one part, a very profound part, but one part of a big enterprise. But by the 1990s, this competition that William Waldergrave, the Minister for Science, made at the time to help him gain money for science in the funding round, he said, if you can describe what the Higgs boson is for me on a single sheet of A4, that might help me present this better in cabinet. And to encourage entries, he awarded a prize of a bottle of vintage champagne. And several people entered for that, and Waldergrave gave the prize out, and that itself generated quite a lot of publicity. I didn't win it, I'll confess that straight out. My entry to him was, I said, being asked to describe, in fact, I think I bypassed it totally. I said, being asked to describe profound scientific ideas on a single sheet of A4 is like Feynman being asked to describe his Nobel Prize in 30 seconds. And he said, if I could do that, it wouldn't have been worth the Nobel Prize. And I said, however, I'm prepared to take the challenge if you can describe for me on a single sheet of A4 the Maastricht Treaty, which was also at that time up in the air. And Waldergrave later very kindly said to me, we both failed each other's challenge. I think was the way it was. But this created publicity. And suddenly, at least within Britain, where the big funding crisis was present, the discovery by media that the idea of the Higgs boson came from a man called Peter Higgs, who was actually a Brit. They thought he was Scottish because he happened to be at Edinburgh University. By the Scottish Peter Higgs, this suddenly created a lot of momentum over here. And Higgs, when I say he was used, I don't mean that in a nasty way, but he certainly became a totem for the whole enterprise, because, as I say in the book, politicians like ready slogans, and as it's easier to follow an individual than an idea. This was how Higgs suddenly became used as the symbol for this quest. And that is in part where I became involved in the early 2000s, because although Peter Higgs is a great scholar and researcher whose expertise is in giving advanced lectures to university students and so forth, his skill in doing public popular expositions is not the greatest. And so the insight was had that perhaps if he were on stage with somebody who he knew and trusted, who could help bring the story alive through him, that is how I got involved. And this was something I'd never done before. The first time we did this was a few months before the actual discovery at a book festival in Scotland. And there was a big tent with a couple of hundred people sitting in it. And I was about to go on. And although I've given lectures for 40 years, I'd never actually interviewed anybody in such a circumstance. Now, one of the people who was at this was Jim Nocte, who of course spent his whole life interviewing people. And I said to him, how do you do this? And he said, well, it's easy. I said, well, it's easy for you, but how do I do this? I said, what would you be asking Higgs if you were doing the interview at this moment? And he thought for a moment, and then he said, I would contextualize it. And I said, well, what do you actually mean by that? And he said, well, is all this business about the Higgs boson a creation of the scientific community? Is it hype and a media creation? Or is it really going to be, would its discovery really be a fundamental moment in human culture? And I thought that's a very good way of really dealing with it, because it was quickly clear to me it would be a seminal moment in human culture. And now the job was for me to articulate why. Why do I believe it's a seminal moment in human culture? How can I bring that across through Peter Higgs to the audience and to the public at large? And although I didn't know it at that time, I suppose that was the moment when the Elusive Book, which I did 10 years later, began to sort of form in my mind. And then over the following months, for the next about 18 months, Peter and I had conversations like that on several occasions. So we spoke before the boson had been discovered. We were together just before the announcement when he got called to CERN. And then I saw him again a month or so later in Edinburgh at the festival after the boson had been discovered. And then we talked again later after he'd been awarded the Nobel Prize. So through these conversations, I built up a timeline of how Peter's feelings were historically, how they reacted to this huge media presence, thrusting this shy person into the limelight, leading up to the announcement of his Nobel Prize. And the way I start the book to bring the elusive out is actually the day of the announcement, because the boson was discovered in 2012, and a lot of people speculated that the 2012 Nobel Prize would go to Higgs. The only other question was who might he share it with? Well, Peter wisely knew that it was too late for that year's Nobel Prize, but from the amount of media reaction, he formed a quick impression of what the real deal would be like if and when the Nobel Prize was awarded to him. So come 2013, when bookmakers were not even taking bets on whether or not it would go to Higgs, he started taking preparations to be out of the way when the announcement was made. And it's well known that the announcement was actually delayed for half an hour because the Swedish Academy were unable to trace him. His colleagues all believed he'd gone off for a holiday in the Scottish Highlands because that's what he had told them he planned to do. Though, as he told me, and the book explains, he realized that all he had to do was to leave his apartment in Edinburgh, Old Town, before anybody was around, when the street was clear, and go off to Leith and go to his favorite seafood bar and have lunch there. And that's what he did. So he was drinking beer and having a seafood lunch while the Swedish Academy was searching for him. He was still eating while the announcement was being made to the world. He then came back home by bus, and he thought it was a bit early, so he went to an art gallery And then finally, as he was about to arrive home, a car stopped, and a woman who knew him said, "Oh, congratulations, Peter. Congratulations, Peter." And he said, "For what?" Of course, he knew what it was. So that's how he learned about it, which is fascinating on many levels, because that also taps in, for me, to Elusive. Because why does one really go to that amount of trouble? And I don't have an easy answer for that. I have several theories of why that might be the case, and I'm sure that you and listeners can think of their own. And I don't think one can ever get an honest answer to it, because to my mind, I try to imagine myself in this situation, and by being absent, you are actually creating an even bigger story, which is the very thing that you supposedly want to avoid. Now, the whole world assumed that Peter Higgs was going to get the prize that year, but I can never know, and maybe Peter Higgs will never know, whether he really believed he would. Until it happens, you don't know for sure. And a very close friend of his, Michael Fisher, whom he had known as an undergraduate at King's College London, who later went to the States, had been very strongly tipped to share a Nobel Prize with two other people, and was devastated when the prize actually went just to one of them, not to him. And that was a cause célèbre, or is a cause célèbre in Nobel history. And I would be surprised were it not the case that Peter Higgs knew in the back of his mind that it ain't over till the fat lady sings, as they say. And so I imagine myself in that situation. What would I have done if it was like that? Well, if I win the prize, of course, I've won the prize. If, however, I suffered the surprise of it going elsewhere, immediately the media would be onto me wanting my comment. And I would want to have time to think how to handle that. And so I think that I probably would have ducked out somehow. But whether that is the reason why or not, we will never know. It's elusive.
It's elusive, just as the title of the book says. And you've captured, I think, very well indeed, that moment that it's a cultural shift as an important point in human history. And I think in Elusive, it tells that story very well indeed. I've only got the preprint copy, but it is an excellently well told.
There's the American version, and there's the
British the American version. I haven't seen that one. But Professor Frank Close, thank you ever so much for your time today and for a fascinating conversation. The book is available as a preprint, not preprint, as a pre-order on Amazon. I believe they're offering.
I think actually, we're doing this interview today, the 14th of June, which is actually the day of its publication in the States. So it should now be available on Amazon as or at any good bookseller. And it's published in the UK on the 7th of July.
That's right, 7th of July. And I believe at the moment they're offering a discount for pre-orders of 22%. So a good time to buy it, which was excellent. Professor Frank Close, thank you very much for your time and for an excellent chat. Thank you.
Thank you.